Tinkering isn't just for 3D printers. Today, we're going to upgrade this 3018 CNC to make it capable of milling acrylic, aluminium, and carbon fiber. This video deals with mains voltage wiring, which has the potential to kill. This is not for beginners. Please consult a professional before attempting these procedures. This is mainly a 3D printing channel, but the truth is that I've been using CNC routers for almost as long as 3D printers. This pic is from the F1 in Schools National Finals in 2015. This is relevant because we started the program in 2013, and machining these little race cars is how I learned about CNC routing. In fact, you can see some old footage of this in my intro. My Chinese 6040 is still going strong in my garage, but it was expensive, especially when getting it shipped to Australia. Since then, I did a series building up a lowrider too, mainly 3D printed CNC build, and I also reviewed this Genmitsu 3018 CNC, which is like a CNC equivalent of the Ender 3, capable and affordable. But that doesn't mean that it can't be improved. So today we're going to modify it to make it more powerful, more refined, tidier, and most importantly, more capable when milling. If you're playing along at home, you can choose which mods you do, whether it be all of them or just some. So let's start by having a look at the plan. The first thing I want to upgrade, because I consider it the weakest link, is the original Spindle. Basically, it's just a 24 volt DC motor and it's limited to 1000 RPM. In its place, I'm going to use a Dremel 3000. This one will set you back around $60 US, but the way we're going to install it means it won't be tied to the machine. You can take it off and still use it as a regular Dremel. Installing a Dremel gives us access to the Dremel ecosystem of cutting bits, but the collet size is the same, so we can still use cheap Chinese bits that come with the machine as well. The cherry on top is that Marcus Gree has already designed a printed mount to suit. In summary, there's a fair few advantages in going with a proven product, and it makes it the best bang for your buck out of everything here. My next upgrade is to the 3 stepper motors that come on the machine, and my choice for replacement are S42B closed loop steppers from Big Tree Tech. They aim to get rid of layer shifts, so for whatever reason, if your printer loses position, these stepper motors will realize it and compensate with a minimum of fuss. I have a full video on this product, and I thank the commenters from that video for suggesting I try this on a CNC. On top of the closed loop feature, they're plug and play, provide more torque, and we get the advantage of setting them up from the screen on the back. Next up, the Mainboard running Gerbil. It works okay, but you have to have the laptop tethered to the machine as you use it, and that means exposing your laptop to dust and debris. There is an offline controller available, but instead I've chosen to upgrade to a 32-bit SKR mini board from Big Tree Tech, and with that, a RepRap full graphic LCD display with SD card. This is a different board to the drop-in E3 models designated for the Ender 3. It's cheap because it doesn't have a MOSFET for a heated bed, but we don't need that anyway for a CNC. The LCD controller is also cheap, but if you're like me, there's a fair chance you have one lying around, or you could substitute the stock one from an Ender 3 or use a TFT touchscreen from Big Tree Tech. This combination means we can ditch the tethered PC and run Marlin firmware. The final area I'd like to improve is the clutter around the machine, and that means eliminating this dedicated power brick. It supplies just under 5 amps at 24 volts, and that's to run the steppers, mainboard, and original Spindle. I'm replacing it with a standalone power supply. It supplies 5 amps at 24 volts, and without the drawer of the Spindle, that should be plenty. I'm going to use a plug-in switch, like from a 3D printer, and I'm going to use a relay connected to the mainboard in conjunction with an Australian standard power point, so I can turn the Dremel on and off without cutting its power cord. I feel this is the tidiest way, but if you didn't want to do it, just plug in the Dremel to the wall and turn it on and off manually. The links for everything you need are in the description, and that includes parts you need to buy, parts you need to print, and the firmware, which is already set up for this combination. I started by compiling the firmware with the newest version of Bugfix Marlin, changing it to suit this mainboard, and then going through and setting it up as a CNC instead of a 3D printer. That means disabling the heated nozzle as well as heated bed, specifying an oversized build volume, and disabling things like software end stops so the spindle can move freely without being homed. I've also set up some custom menu items for zeroing axes, moving to 0, and I've set it up so you could run additional relays for things like mist and flood control. In the pins file, I've added comments to explain what I've done, for instance using the Xmax end stop port to control the relay for the spindle. This compiles fine using the 512K option in the Marlin Firmware Auto Build plugin, and this branch of Marlin is available for free by going to my GitHub, which is linked in the video description. With the firmware flashed, I built and tested the relay circuit on the bench, which was working as it should be. I then took the components and started to mock them up, experimenting with different mounting positions on the CNC frame. And here's what I came up with in CAD. If we hide the lid, we can see inside, and turning on one of the main sketches will show you where everything's positioned. Our main board is over on the left hand side, with openings for the USB and SD card. The power supply sits firmly in the middle, the relay sits next to that, and the PowerPoint rests on top. The plug comes in on the right hand side, which means all of our mains wiring is contained to one area. On the front corner we have mounts for the LCD, and in the middle a slot for a PTFE tube cable guide. For the case, I used almost all of the parts of this excellent design from Mighty Nozzle, but remixed my own base with a matching hinge for the electronics case. We start by checking the 3mm holes and drilling them out if they're undersized, and then we mount the power supply, sliding it in from the side to avoid the upper tab. We adjust its position until the 4 mounting holes line up, and then it's very important to use the shortest M3 bolts possible so that they don't extend too far into the internals of the power supply, in which case the power supply becomes incredibly dangerous. We can now insert the plug and switch using 2 more M3 countersunk bolts to hold it in place, and following that we can mount our twin relay. The reason I'm using a twin rather than a single channel is that it was the only relay I had on stock that's active low. You can see here I've connected 5 volts and ground to the relay, and the green wire is also connected to ground, and when I touch it on the input pin it triggers the relay. If I attach 5 volt to the input pin, nothing. And that's exactly what we want. You might have noticed that fans and other items on your 3D printer get full power when the printer first turns on. By using an active low relay, we still have full control of the spindle from the firmware, but it won't spin up when we don't want it to, and pressing reset will cut it off as well. The relay is mounted with 4 M3 bolts that cut their own thread into the electronics case. Next up, the case needs to go on the machine, so we need some short M3 bolts as well as some T-nuts, and you can use up to 8. We simply line up the T-nuts with the existing 2020 extrusions and then torque up the bolts to hold everything in place. Now the main board can be inserted, and once again we use short M3 bolts that cut their own thread into the electronics case. With all of the components in place, it's time to do some wiring, and that includes mains wiring, hence the disclaimer at the start of the video. The mains wiring is fairly simple. Out of the switch we run into the power supply, but then we daisy chain earth and neutral straight to the power point. The active wire, however, goes into the relay, connected to closed and normally open, the other end going up to the power point. The wiring on the low voltage side is also pretty simple. We have 24 volts and ground in from the power supply, and then the Xmax end stop port connects to the relay with 5 volts ground and signal. Optionally, the firmware is set up to control 2 more relays from Ymax and Zmin. One more thing to note is where to insert the jumpers, which are marked here in blue. They will permanently trigger the end stop pins, which means if we accidentally select auto home, we won't have a collision. For the mains wiring, I strongly recommend using crimp connectors. For the connections to the power switch, these female spade connectors fit perfectly. This connector goes perfectly onto the power supply, and as you can see we can input 2 cables to make our split. And for the back of the power point, these male bullet connectors fit perfectly too. Finally, for our connections going to the relay and the main board, these crimp-on ferrules will get the job done. And here it is all wired up with our long mains wires hanging loose, ready to thread through the lid and into the back of the power point. Now's a good time to assemble the RepWrap LCD. There's this spacer part to prevent the PCBs from flexing. The controller then sits inside my remixed base. With the reset button in place, the lid then slides down over the top, and M3 hardware is inserted from the rear. The threads are already designed into the upper piece. Push the click wheel into position and our assembly is done. The printed hinges should now line up for the two parts. M5 bolts secure it from either side, and if it's still too flimsy, a third one comes in from the top to support the LCD. We now feed any wiring for the LCD through the top hole down towards the mainboard, and it's also time to feed in the 3 wires that will go to the stepper motors. X and Y come through the bottom hole, and Z comes in through the top. That's all of the internal wiring done, so we can feed through our 3 mains wires that go into the back of the PowerPoint, and then use 6 M4 bolts to secure the lid, cutting the threads as we go. Our PowerPoint connections can now be inserted and tightened into the back of the PowerPoint before it too completes the assembly by slotting into place with M3 bolts cutting their own thread, securing it into position. I noticed I made a mistake on my printed version and had to trim the corner of the PowerPoint, but I've adjusted this for the version on Thingiverse so you won't have this issue. That's the main board and the internal electronics case wiring complete. Before we continue, now's a great time to test the wiring by turning on the spindle, the PowerPoint, and then using the spindle control commands on the LCD to make sure it turns on and off as we would expect. Time to swap out the stepper motors, and to do this we need to loosen the 2 grub screws on the shaft coupler, and then loosen the 4 M3 bolts that hold it onto the frame. With all of this undone, it should pop right out. Now as you can see, the shaft on the S42B steppers is around 10 mils longer, and that stops it from going the whole way into the coupler. To combat this, I designed this series of 3 spacers to be printed in PETG or other temperature resistant filament. With the spacers in place, M3 by 25mm bolts should be the exact length to hold everything securely. The last thing we need to do is adapt the Z mount to hold the Dremel, and I followed the instructions for that thing, printing it in PLA with extremely high infill, although I did forget to leave the light on for my octolapse. The bolt and square nut that tightens down the standard motor can be removed, and this is transported over to the new part to hold the Dremel in place. The old motor slides straight out, and there's another 4 M3 bolts holding in the top stepper motor, except these ones are a lot harder to access. But when you finally get them, the old stepper motor will lift straight off. Most of the parts for the Z assembly are pressed into place, so with some firm pressure you should be able to remove them. But all we really need is enough clearance to remove the old motor mount. It's time to transport the bearings and lead screw nuts into the new printed part. The old bearings press out easily enough, but because the new printed part is thinner, you'll find the old bearings are too tall. Fortunately, I had the correct size bearing sitting as a spare part in my drawer. These should be a tight fit, so you should be able to hammer them into position, but be warned that if your printed part is too small, you'll probably crack it from doing this, and you should drill it out closer to the correct size first. One of the lead screw nuts simply turns out, but there's another one still embedded in the part. The second nut was molded into the plastic. I found the only way I could get it was to use a vise to slowly press it out. After it's out, we need to position it on the top side of the new mount, before using a hot soldering iron to melt it down into place. The PLA plastic will go pretty soft, which means you can remove the soldering iron and use something flat to push it down flush with the top of the part. We finish our sub-assembly by inserting the spring, the second lead screw nut, compressing the spring, and then screwing down from the top with the lead screw until the thread catches. Reinstallation is the exact opposite of before. We feed it into position and then use something flat to push down the rods, and you may find it easiest to put the machine on its side so you can check the alignment of the rod bottom before you apply pressure. Just like the X and Y axes, we use the printed spacer to get the stepper motor in the correct position, and optionally you can use some spare PTFE tube as a cable guide. One thing I didn't like on what's meant to be a robust machine was how exposed the electronics of the S42B were, so I designed this simple clip-on cover to prevent damage to most of the delicate bits. It's a simple press fit and can be removed if you need to access the buttons. When starting out, the steps per millimeter for each axis in the firmware was all over the place, and there are 3 methods you can use to determine the correct value. The first is to line a ruler with one of the moving parts, move it by 10 mils, and measure how far it actually moves. The second method is to use some digital calipers, zero them, and then move the carriage against them to measure exactly how far it moved. And the third is to use a dial gauge in the same way, which gave me the same measurement of 5.9. After crunching the maths, I used the LCD to set the final value to 509 for each axis. And this is to match the S42Bs being set on the LCDs to 1/8 microstepping. After verifying my values with the dial gauge, I then stored them to EEPROM. And that is everything 100% assembled and set up, which means we can finally use the machine. Now you would have noticed that this electronics case is long, 380mm in fact, so you're going to need a pretty big printer to be able to print it. However, I have included the source files for the design, that way you can segment it into smaller pieces to fit other machines. Anyways, time to test performance, and originally this machine is marketed more as just a surface engraver, but what I'm really interested in is milling some tougher materials, so let's start simple and work our way up to that. The free and cloud-based CAM software that I'm using is called Kirimoto, and I covered this in detail in earlier videos. It has, however, had a lot of development recently, including things like toolpath previews for CNC routing. If you'd like to see an updated guide for this great free software, then let me know in the comments section. Before starting the job, we need to make sure the power point for the Dremel is switched on, and that we've also set the rotational speed on the front of the Dremel. We use the move controls on the LCD to lower the Dremel into the starting position, and then we use the zero all axes button to tell the machine it's at 000. With our G-code on the SD card, we can now start it exactly how we would start a 3D print. I used a mangy old piece of testing acrylic and quickly realized the Dremel should be on the highest speed. After this, it cut quite well with a 1mm pass depth and a feed rate of 400mm per minute. After the job finished, I removed the part, did a little bit of tidying up, and the result was clear. The CNC router was working as it should. So I graduated to a clean piece of 3mm acrylic and started the same G-code again. The result is another really clean part, with nice edges without the need for any sanding. So acrylic, like before, is a piece of cake, so let's try out some aluminium. When I reviewed the machine stock, I was able to use water to keep the bit cool and cut through aluminium, albeit very slowly. This time I had the proper equipment for the job, which was a can of spray-on cutting spray. This keeps everything cool, catches the chips and prolongs tool life. This time around I ran 1/4mm passes at a feed rate of 200mm per minute, and honestly the machine seemed to do quite well, so I would feel confident about being more aggressive in future. The final product is once again something I'm very happy with nice clean edges without the need for any post-processing. This machine was performing very well. Success so far, so let's escalate things with some carbon fiber sheet as requested by one of my patrons. Now a reminder that the dust from this stuff is particularly bad, so please use extraction and wear a respirator. I googled whether cutting fluid is suitable for cutting carbon fiber sheet, and the answer seemed to be yes, so I used it, if only to try and capture some of the dust. Starting the job without the cutting fluid, you can see just how much debris and dust is spread around the machine. And when I saw that, using cutting fluid was an easy choice. For the carbon sheet, I ran the same parameters as I did for the aluminium, 1/4mm passes at 200mm per minute feed rate. The only thing I adjusted was the overall depth to suit the 4mm carbon sheet as opposed to the 2mm aluminium. As the machine steadily worked its way through layer by layer, you could see that the cutting fluid was doing a pretty good job of collecting a lot of the debris. You definitely want to take every step that you can to minimize the amount of airborne fibers. This is another result that I'm super happy with. We've got very clean edges without any sanding, and the top and bottom surfaces are perfectly intact. Carbon fiber can easily splinter if not cut correctly. This is only a simple test piece, but I think it's a proof of concept to show that you could cut something much more complex, like a carbon fiber frame for a drone. So far, I was really happy with the performance, but I did need one more test, something that ran for a long time to see if the Dremel will get hot and melt the PLA mount. To achieve this, I got a suitable picture from Initial D off the internet and set up the machining of the surface using very fine 0.5 mm increments. This was perfect as the machining time was a little over 2 hours. The result, however, was pretty average because I was experimenting with a different Dremel bit rather than the engraving bit that I would normally use. The natural features of the timber also obscured the image. Not the best final result, probably because I cut corners in the prep and I didn't really use the best tool, but in terms of testing whether the Dremel gets hot, it served the purpose, and I'm pleased to report there was no such issues, which makes sense since it's a handheld tool. I'm really chuffed with how this turned out, so let me know what you think, especially if you've got some more great ideas on what I can modify further. And of course, all of the source files are available, so please tweak and remix away. Thank you so much for watching, and until next time, happy CNC machining. G'day, it's Michael again. If you like the video, then please click like. If you want to see more content like this in future, click subscribe and make sure you click on the bell to receive every notification. If you really want to support the channel and see exclusive content, become a patron. Visit my Patreon page. See you next time.